Let's take a look now at section 9.1 about sequences. So let's go ahead and begin with a definition. All right, so definition. Let f be a function that maps, let f be a function that maps the natural numbers to the set of real numbers. That's typically denoted as f maps the natural numbers to the real numbers, or at least some subset of the real numbers. Not every real number needs to be covered here. Then f is a sequence where f of n is referred to as the nth term of the sequence for n a natural number. So for any natural number n. Okay, so note that your function is a mapping. It's a function, but the domain of the function is the natural numbers, 1, 2, 3, 4, 5, and so forth. It maps to the set of real numbers. Now, of course, here the mapping doesn't have to cover all the real numbers. Not every real number will be used. So here what we're defining is a sequence, and we're defining the nth term of a sequence. Okay? So one example would be something like this. Now, when we deal with functions of the natural numbers, it's typical not to use f of x, but f of n to denote the fact that n should not be any number, but rather a natural number. So here, for example, you might say f of n is equal to, let's just keep it simple. Let's say 2n plus 5. All right, so there's a function. And notice this maps every natural number to some element of the real numbers. Now here, the results of mapping the integers, mapping the natural numbers are other natural numbers, and that's fine. These can be natural numbers or fractions or anything else. So here, if this is a function, even though this function does define a sequence, it's often common to write a sequence out by writing out a sequence of, for lack of a better term, a collection, an ordered list of terms. So here, this is our function. F of 1 would equal to 2 times 1 plus 5, which is, well, 7. F of 2 would equal to 2 times 2 plus 5, which will give us 9. F of 3 and F of 4, those would be 2 times 3 plus 5 and 2 times 4 plus 5. Or in other words, they would be 11 and 13. So this would be the first term of the sequence because it's the element that we get when we take f of 1. So this is the first element of the sequence, the second element, the third element, the fourth element. When you have an arbitrary element, in other words, you don't know if it's the first, second, third, fourth, fifth, and so forth, well, then the n would be left in place, and this would be 2n plus 5. So this is the first element, or the first term, as it's often called, the second term in the sequence, the third, fourth, fifth. If you have an arbitrary term, that's called the nth term. Anyone who ever plays Scrabble, NTH is a perfectly valid word, and don't let my sister tell you otherwise. F of n plus 1, well, that would be 2 times n plus 1 plus 5, and this would be the n plus first term. Okay, things like that. So here, it is common to write the sequence not in this notation, although this can be used, but in a subscript notation. What I mean by that is here, this is the first, the second, the third, the fourth, and so forth. So we often write this as a sub n is equal to 2n plus 5. Instead of writing it as a function, we'll write it using subscript notation. And when we write out the actual elements of a term, a sub 1 is equal to 7, a sub 2 is equal to 9, a sub 3 is equal to 11, a sub 4 equals to 13, and so forth and so on. It is common to simply write these as a list. So here a sub n could be written as 2n plus 5, or it can also be written as the list 7, 9, 11, 13, comma, dot, 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 because of course that does keep on going. The domain of this is all natural numbers, and so of course there is no end to the natural numbers. So there's a first one, a second, a third, a fourth, but there is no last. And here we could write this as a set of numbers. Notice this is an ordered set. There is a first element in the set, there's a second, a third. Changing the order changes the set. All right. So here a simple question might be something like, list the terms of the set. And again, the set is a function, but it's typically written in the subscript notation. So here we can write this as a sub n is equal to 2 to the power n minus 1, like this. And here we would just write this out as, well, the list of the are, so here, the terms are given by, and here it's just a matter of substitution. You start with 1, so that's 2 to the first minus 1 is 1, 2 to the second minus 1 is 3, 2 to the third minus 1 is 7, 2 to the fourth minus 1 is 15, and so forth and so on. Obviously, you never write out all the terms. It's typical to write out the first 4 or 5 terms, because by then either you see the pattern, or the pattern is so complicated it's something that's not easy to see anyway. So we would probably want to leave it this way. Note that the A doesn't always have to be an A. We can often distinguish between different sequences by using a different label, just like when we have function notation, F and G are used for 2 different functions. Here we can use A or B or C. So for example, another example would be we could list the terms of the set. I guess it should be of the sequence, not, it is a set, but let's be a little more specific. Sequence. Here, let's say B sub n is equal to, and of course these don't have to be whole numbers or integers even. We can have something like, let's say 2 to the power n over 3 to the n minus 1. And again, the terms are, and it would just be a matter of substitution. You always know which one the first is. You plug in 1. So 2 to the first over 3 to the first minus 1, that's 2 over 2. And of course, you could always write that as 1. Comma, let's see, if we have the second power, that's going to be 4 over 9 minus 1 is 8, and that works out to be a half. The next one would be 2 to the third power, which is going to give me 8. 3 to the third is 27 minus 1 is 26. And of course, you can reduce that, divide top and bottom by 2. And then the next one would be the 2 to the fourth power is 16. 3 to the fourth power is 81. Minus 1 is 80. And it looks like the top equals. It looks like the top and bottom there can be divided by 16. So that'll leave me 1/5, and so forth and so on. Like that. Now, a sequence on its own is not particularly interesting. It's quite literally a list of numbers. What is a little more interesting is what happens to these numbers as your terms grow, as you have not the first, the second, the third, the fourth, but the nth. an arbitrarily big natural number substituted into your function. So here, let's give another definition. Let's begin with let L be a real number and A sub n be a sequence. A little bit in terms of the notation here. If we write A sub n without the braces, that means the nth term. In other words, that's the first term or the second term or the third term. If we write A sub n with the braces, that means the sequence made out of those terms. So here, that's a bit of notation. It's not really part of the definition, but it is important to make sure we understand what we're talking about when we write a certain symbol. Here, this is the nth term. All right? The first or the second or the third or the fourth. If you write it with the braces, then that's going to be the sequence. All right? So in other words, this one would be, what's the fifth sequence? Well, sorry, what's the fifth term in the sequence? Oh, it's the number 5. Okay, what are all the terms in the sequence? Oh, they're 1, 7, 9, 3, 5, 4, 12. This one is a list. This one's just a single one. Single element versus a list of elements. That seems like a mild distinction, but if you don't make that distinction here, this kind of sounds very, very strange because you're saying, oh, if something happens to this, then something else happens to this. But if you think they're the same thing, well, that's nonsense. But here, they're related to each other, but they're not the same. All right, so here's our definition. Let L be a real number, and let A sub n in braces be a sequence, the whole list. If for every epsilon greater than 0, there exists a number, and this is just a regular number, greater than 0, it's a positive number, such that the absolute value of A sub n minus L is less than epsilon, whenever n is greater than m, then we write the limit as n approaches infinity of A sub n equals to L. If the limit exists, we say that the sequence converges to L. Not the individual terms, but the actual sequence. Otherwise, we say that the sequence A sub n diverges. This should sound very familiar. This sounds an awful lot like our definition of a limit of a function back in Cal 1. Here, a lot of the same ideas hold, and as we'll see, a lot of the same things will be useful in evaluating our limits. But there are a few distinctions here that are different. Let's take a look at an illustration to highlight what those are. First of all, your function is no longer continuous. It is discrete. You no longer have a collection, you no longer have a smooth, continuous curve, but now you have a collection of discrete points, individual dots, right? There is a first one. There is a second one. There is a third one, a fourth one, a fifth one, a sixth one, a seventh, an eighth, a ninth, a 10th. There are points that are separate from each other. There's no line connecting these. These are individual discrete points. Here, if n is equal to 1, then f of n is equal to that. If n is equal to 2, then f of n is equal to this. All right. So here, that's a set of points. All right. So first of all, that's what we have here. We have a sequence, and this would be the graph of a sequence, separate points. Now, we have L is a number. Okay, well, for this illustration, it would be this number right here. So let's see here. That's going to be, I'll call this my L. And that's really just a number. All right, now, we want to say the limit as n approaches infinity of this sequence is L. Well, how do we know we can say that? What does that mean? Well, it says, if for all epsilon greater than 0, epsilon is just a number. It's a very small number, though. So when you see epsilon, that's meant to be a small number. And when we say small, we don't mean like 1 or 2. We mean like 0.0000000001. Some very, very small number. There exists another number, m, which is also positive. Here, this m Again, it's just a number, but it's not just any number. We typically mean for it to be a big number. What do we mean by a big number? Well, that kind of depends on the sequence. In some cases, it'll be 50 or 1,000 or a million. Don't worry, you don't really need to figure out what this number is. We just need to know that there is one. All right, so if for all epsilon greater than 0, there exists an m greater than 0, such that, well, let's see, a sub n minus L. Well, a sub n is the nth term of the sequence. Here, if you imagine this is the xy plane, that's the y value of each of these points. So what this is saying is that the absolute value between a sub n and L, or in other words, the distance between a sub n and L, is less than epsilon. Okay, visually what that means is, if this is your L, pick a small little neighborhood around L, meaning pick just a small little interval so that the maximum you go away from L is that little tiny number epsilon. L plus epsilon would put you above L, and L minus epsilon is below L. But again, remember, this is a very tiny number. So if this is 50, this would be 50.0001, and this would be 49.9999. Okay, so if for every epsilon, here it doesn't matter what these numbers are, anyone should work, there exists some number m such that the distance between here and here is less than epsilon. Okay, so I want my distance to be less than that distance there. Whenever n is greater than m, what m means is, notice, my sequence comes in and out of this range. What I'm trying to do is I'm trying to keep my points, the y values of my points, within this little neighborhood around L. Well, notice it doesn't do that, at least not at first. This one's outside the interval, and that one's outside. But now this one's inside. Oh, but now that one's outside again. And that one's inside, and that one's inside, and that one's inside. Oh, but that one's outside. Oh, but starting from here and on forever, my points are now inside this interval. So that's what we mean by m. What we mean is, okay, this sequence, I know it goes up and down, back and forth, whatever. But it looks like it's getting closer and closer to this line, the one in the middle. You say, well, how can I confirm that? Well, if you can get to a certain point where once you get past that point, your sequence never leaves this neighborhood, this little interval, then that means that your limit will converge. But there's nothing special about this epsilon. This has to work no matter what. So here, if I pick the smaller epsilon, then, okay, it might take me longer to lock my sequence inside of that neighborhood. All right? It's a harder condition to fulfill. But either way, no matter what my epsilon is, no matter how small I make this little neighborhood, I should always be able to find, okay, here my function's going in and out and in and out and in and out, and here it just barely is outside. Oh, but once I get past this point, then that means that my sequence is always inside that interval. So for every epsilon, no matter how small I make this, I should be able to search for a certain point where once I get past that point, my sequence is stuck inside that interval and never ever leaves. If that happens, then we say the limit as n approaches infinity of a sub n is equal to L. Now, this does sound an awful lot like the limit of a continuous function. Well, yeah, but this isn't continuous. After all, this is discrete. Well, yeah, but if I connected the dots, it would be continuous. Yeah, if. Well, why not? This brings us to a theorem, which says, let's begin with L as a real number, and let's let f be a function of also a real number. So let f of x, notice that's not f of n, that's not a natural number, that's just any old number. Let f of x be a continuous function. So not a bunch of points, but actually just a normal function, the kind that we're used to. let's let L be a real number. And let A sub n, and that's a sequence, let A sub n be a sequence whose nth term is f of n. Or in other words, if you have to find the first term of your sequence, you can just plug one into the regular continuous function. If you wanted to find the second term of your sequence, well, you could plug 2 into the regular continuous function. Now, you could plug in 1/3 into the regular continuous function, and that would be fine, but that wouldn't be one of the terms of your sequence. All right? That's not saying this is always a term of a sequence. That's saying if you plug in a natural number, this will give you the nth term of the sequence, whose nth term is f sub n. All right? If the limit as n approaches infinity of f of x is equal to L, then the limit as n approaches infinity of a sub n will also equal to L. Just like that. Here, we're not going to prove this theorem, although we're going to motivate it. We're going to go ahead and illustrate what it's saying and suggest why it should be true. The formal proof of this is, we're not going to go through all of it. But essentially, it says the following. Okay, you're back in Cal 1, and you are going to find the limit of a continuous function. Okay, well, here's a continuous function. Now here you have a continuous function that has a limit. No fair having one that oscillates or one that goes to infinity. It actually should, if it's going to oscillate, it should still end up with a limit. So let's say I have a function that looks like this. Okay, so here that function seems to quite clearly converge to this number L. All right, after all, it does eventually start to follow that black line. So now, let's say we took a sequence out of the values where x is equal to 1 and x is equal to 2 and 3 and 4 and so forth. So here, let's say that's 1 and 2 and 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, like that. All right, well now here, if I took the points on the curve that correspond to x is equal to 1 and 2 and 3 and 4 and 5 and 6, 7, 8, 9, 10, 11, 12, 13, 14. If you look at just those individual points, well, notice those points are restricted to that line. Those blue points are restricted to that red line. Well, yeah, but that red line has no choice but to eventually conform to the line y equals to L. Well, yeah, but if those points follow the red line, then they also have no choice but to eventually conform to L. So that's what the theorem is saying. It says, okay, if you have a continuous function, that's your red line here, that's your f of x, and you have a sequence that is made up of the discrete points of that function, and L is just some number, then and let the sequence be defined as points on that curve, then if the curve converges to L, if the function converges to L, then the set of terms also has no choice but to converge to L. Note that the opposite is not true. If you have this converging to L, that doesn't say anything about this one. Here, you can have a situation where your individual points are converging. In fact, here, let's have a sequence where all the terms, not only are they converging, they're constant. Here, every term is equal to, let's say, 1. All right, so a sub 1 is 1, a sub 2 is 1, a sub 3 is 1, a sub 4 is 1, equals 1, a sub 2 equals 1, a sub 3 equals 1, and so forth. This is the sequence that's very, very boring. It's 1, comma, 1, comma, 1, comma, 1, comma, dot, dot, dot. All right. That clearly converges because, well, it's constant. That doesn't mean that the function that this came from is going to converge. Here, my function might look like this. It could oscillate up and down forever and ever and ever. And if a function oscillates forever and ever and ever, then it will not converge. So note that the opposite is not true. If the continuous function converges, then any points restricted to that continuous function must converge. The opposite is not true. If the individual points of your sequence converge, that doesn't tell you anything about your overall function. So just be mindful of every time you have a theorem, there is a particular direction. If this, then I know this. Doesn't say anything about the opposite direction. So as a quick example of that, we could say, go ahead and find a limit. Find the limit as n approaches infinity of 4n minus 1 over 4n. What this previous theorem tells us is that if we know something about the limit of a continuous function, then we can figure out something about the limit of points, discrete points, from that function gives us. But we know a lot about the limit of continuous functions. Right? We went through all of Cal 1 and saw how to evaluate limits. And in Cal 2, so far, we've seen a few other techniques to evaluate limits. In particular, L'Hopital's rule is very, very handy. So here, I may not know anything about discrete functions. I may not know anything about sequences. Well, yeah, but I know a lot about continuous functions. So here I can say, well, consider the function f of x equals to 4n minus 1, 4x minus 1 over 4x. I know everything about that one. If I want to take the limit as x approaches infinity of 4x minus 1 over 4x, if we were in Calculus 1, we could divide everything by x, divide the top and the bottom by x, and we could evaluate that way. But since we've seen L'Hopital's rule, we can even do it a little bit shorter. We can say, oh, look, by L'Hopital's rule, we know that that's the limit as x approaches infinity of 4 over 4, because that's the derivative of the top over the derivative of the bottom, which, of course, gives us the limit as x approaches infinity of a constant 1, which is 1. But, of course, over here, if you take the first, the second, the term, if you take the nth term of f of x, that would just be 4n minus 1 over 4n. So here, not only do you have a continuous function whose limit you know, but by plugging in the integers into this function, here you'll note that f of 1 is the same as saying a sub 1. And if you plug in 2 into this function, that would be the same as if I said the second term of the sequence, a sub 2, and so forth and so on. So this satisfies the condition of my theorem, which says, okay, plugging in the natural numbers here gives you these terms, and this one converges, which means this one must converge. So the limit as n approaches infinity of 4n minus 1 over 4n is equal to the number 1. At this point, I have people protest and say, well, wait a minute. Why did I have to go through this? Couldn't I just have used L'Hopital's rule on this? No, you can't. Because remember, this is not a continuous function. L'Hopital is defined, so L'Hopital's rule is defined by using continuous functions. Here, this is a discrete set of points. How do you take the derivative of a function that's made up of a discrete set of points? Here, when I have a continuous function, I know how to describe a derivative. How do I describe a derivative of just the individual points? I don't really know, because after all, a derivative is defined by taking the limit of the difference quotient. But in order for the limit of the difference quotient to exist, you have to have these points getting closer and closer together, which means you need this function to be continuous between these 2 points. If you don't have this stuff in the middle, derivatives can't be defined, which means that taking the derivative of this is not possible because this is not continuous. But if taking a derivative is not possible, that means L'Hopital's rule is impossible. So here, this actually is necessary because here, L'Hopital's rule is undefined. But of course, L'Hopital's rule is not the only way things can work. So if it's not exactly convincing here that you say, oh, well, there's a major difference between these, maybe this next example will highlight that a little bit better. Let's talk about this example. Let's find the limit as n approaches infinity of n minus, that should be n plus 1. Let's talk about, that's n minus 2. So let's take a look at n minus 2 factorial over n factorial. And at this point, any thought of L'Hopital's rule goes right out the window. Because what is that? The factorials. For those of you who may not remember or may not have seen these for a while, we see these in pre-cal a bit. The factorial, n factorial, is defined as n times n minus 1 times n minus 2 times ... all the way till you get down to 3 times 2 times 1. Like that. So for example, if you had 4 factorial, that would be 4 times 3 times 2 times 1. If you had 5 factorial, that would be 5 times 4 times 3 times 2 times 1. And I have no idea how I would take the derivative of this. You say, well, yeah, because you said that they were discrete points. If I just make this an x, if I make this continuous, then that'll work, right? Right? Yes, please? No, that doesn't work. I've never seen this before, at least not in Cal 1. How do you take the derivative of that? The answer is you don't. Right? Here, this is not defined for a continuous function. Now, I take that back slightly. There is a way of defining the factorial as a continuous function. It is not nice. Anyone who has some free time, and since you're on a computer now anyway, you might look up the gamma function, G-A-M-M-A, and it gets very, very messy. In any event, it's not necessary here. Limit as n approaches infinity of n minus 2 factorial over n factorial. There are other ways of evaluating a limit. Here, in Cal 1, we saw plenty of times where we never even had L'Hopital's rule. What was required to evaluate a limit was to simplify. We were not using calculus, we were using algebra. So here, L'Hopital's rule is not valid, it's not possible, but we can still do this. Because after all, n minus 2 factorial over n factorial. Notice that I can take n factorial and I can write it out a long way like this. I can have that denominator, oh, I can barely even see that, right? Okay, as n, right, by definition, n factorial is n, times n minus 1 times n minus 2 times n minus 3 times ... until I get down to 3 and 2 and 1. Okay, very nice. Oh, but now, this is n minus 2 factorial. And remember, the way factorials work is you start with that number, and then you just start counting down. So n minus 2 factorial is n minus 2 times n minus 1 times n minus, what am I doing? I'm supposed to be subtracting 1. So n minus 2, n minus 3, n minus 4, and so forth and so on, ... until eventually I get to 3, then 2, then 1. Just like that. All right? So start with n minus 2. If I subtract 1 from this, that's n minus 3. If I subtract another one, that's n minus 4, n minus 5, and so forth, until eventually I get down to 3, 2, and 1. But you notice now, a bunch of these things divide away. After all, these are just factors. So here, this reduces down to give me the limit as n approaches infinity of, well, now all those divided away, so I'm just left with the number 1, right? This over this is 1, this over this is 1. They're all 1. And in my denominator, I'm left with n times n minus 1, or more simply, the limit as n approaches infinity of 1 over n squared minus n. Oh, but now that one, I know how to turn into a continuous function. So notice, the algebra first requires us to simplify. Once we simplify, then we know what to do with this one. You say, okay, now I can use L'Hopital's rule. No, there's no need for L'Hopital's rule. We know how to do that one. So now consider the continuous version of this. Let's consider the limit as x approaches infinity of 1 over x squared minus x. Here, as x approaches infinity, this approaches infinity. And as this approaches infinity, 1 over this will approach 0. So here, this will converge to 0. But since this is the continuous version of this, that means that this limit will also converge to 0. So here, our limit as n approaches infinity of n minus 2 factorial over n factorial gives us 0. Finding the limits of sequences will be something really rather central to what we'll be doing throughout this chapter. Now, this may seem a little different from calculus as we're used to. So far, we've been looking at methods of integration or differentiation. This doesn't seem to have anything to do with either of those. Here, we have limits, but none of the other stuff that we're used to. Well, yeah, but remember, derivatives and integrals are defined using limits. Right? So here, we're going to be able to use this a little later for some things that start to look a lot more familiar. But first, we need the tools to do that with. Let's go ahead and now talk about some properties that are going to help us find limits. Because, of course, if we can think of a function as being, oh, this is just the discrete case of this continuous function, okay, great. Oh, but if I can't, oh, well, then I can simplify and then think of it as a discrete case of a continuous function. Well, maybe, but maybe not. So here, let's take a look at some properties of limits that are going to help us in evaluating some of the more challenging ones. Here, the limits themselves don't have properties that are unfamiliar. In fact, we're going to start off with just linearity. So this is a theorem. We begin by defining a couple of sequences who have limits. So let a sub n and b sub n be sequences. So the nth term of this is a sub n, the nth term of this is b sub n, such that the limit as n approaches infinity of the nth term of the first sequence has a limit L, and the limit as n approaches infinity of my nth term of my second sequence is equal to k, where L and k are real numbers. Okay. Then the following things are true. Property number 1 says the limit of the sum is the same as the sum of the limits. So limit as n approaches infinity of a sub n plus or minus b sub n, that's going to equal to the limit as n approaches infinity of a sub n plus or minus the limit as n approaches infinity of b sub n, or in other words, just L plus or minus k. So if you're going to take the limit of a sum, that's the same as the sum of the limits. If you're going to take the limit of a difference, that's the same as the difference of the limits. Number 2 says if you're going to take the limit as n approaches infinity of a constant, I guess I should have defined that up here too, where C, L, and K are real numbers. So here, if we take the limit as n approaches infinity of a constant, a real number, times a sub n, that's the same as taking the limit as n approaches infinity of a sub n times c, or in other words, it's equal to c times L. And just like many of the other operations that we've seen throughout calculus, this has the linear property. All right? So here, the limit is a linear operation, just like it was for a continuous function. Property number 3 tells us that if we take the limit as n approaches infinity of a sub n times b sub n, that's going to be the limit as n approaches infinity of a sub n times the limit as n approaches infinity of b sub n, or in other words, it's just L times K. And finally, for the quotient, if you take the limit as n approaches infinity of a sub n over b sub n, that will be the limit as n approaches infinity of a sub n divided by the limit as n approaches infinity of b sub n, or in other words, it'll be L over K, and here provided that K not equal to 0. Because of course, if it is equal to 0, this whole thing is nonsense. Provided that K not equal to 0. All right? And if this theorem sounds familiar, it's because it is. It's the same theorem that we had for the limit of continuous functions back in Chapter 1 of Calculus 1. In fact, we're going to see another theorem here, which also is the discrete version of a continuous case. You'll notice we're not going to prove these because, again, they are simply the discrete versions of the continuous case, and so we're not going to see too much different because we're going to end up with the same results. So, theorem. And this is the discrete version of the squeeze theorem. The squeeze theorem for sequences. The squeeze theorem says, let's begin with a couple of sequences. Let a sub n and b sub n and c sub n, so it's not a couple, we're going to have 3 sequences. Let a, b, and c sub n be sequences such that, and here we have a few conditions, the limit as n approaches infinity of a sub n should equal to L. The limit as n approaches infinity of c sub n should also equal to L. So these aren't 2 different numbers. They are the same thing for a real number L. And one more thing, the nth term of B should be between the nth term of A and the nth term of C. So such that A sub n is less than or equal to B sub n, which is less than or equal to C sub n. If that's the case, then it must be true that the limit as n approaches infinity of b sub n must also equal to L. The illustration for that is really just the squeeze theorem as we're used to it from Cal 1. If you have a couple of sequences, one of which is, if you have 3 sequences, one of which looks like this. Okay, well, clearly that's converging to that number, whatever that number L is. And let's say I have another sequence, which is converging to that same L, but in a different way. Okay, so here this would be our sequence C sub n, and this one in red would be our sequence A sub n. All right, so here we have two sequences, both of which converge to L, to that same number. Now, let's say we have a third sequence that is locked in between those. So the biggest it ever gets is A sub n, and the smallest it ever gets is C sub n. It doesn't have to ever meet those, but it should be locked in between them. So here it doesn't matter what happens to these points. If we know that they have to be locked in between the upper and the lower bounds given by those sequences, then that means that this has no choice but to also be squeezed in here and to converge to L. All right? So here, this in black would be our sequence B sub n. And of course, our sequences don't have to converge exactly like this. Here, this is just for illustration purposes, but the squeeze theorem applies to any collection of sequences where these conditions hold. So for example, let's consider the sequence given by -1 to the power n over n. And here we're going to say, let's take the limit as n approaches infinity of that. Okay, well, that looks a little strange. Well, let's see what that looks like, though. Here, I'm going to list out the first few terms of this. So if I'm going to write out the sequence -1 to the power n over n, well, let's see here. That's going to be, if I use n is equal to 1, -1 to the first is -1 over 1. Okay, so that's -1 over 1. Comma. If n is equal to 2, -1 squared is +1 over 2. And then if n is equal to 3, -1 to the third power is -1 over 3. And then fourth power, well, that makes it positive again. And then fifth power makes it negative, and then positive, and then negative, and so forth. This is going to be a term that's convenient to us throughout this chapter. Anytime you need a set of terms to oscillate between positive and negative, -1 to the nth power will do that for you. That'll come in handy later on down the line. Okay, so now we see the pattern here. It's just plus, minus, or I suppose minus, plus, minus, plus, minus, plus, and then the denominator is just 1, 2, 3, 4, 5, 6. Okay. Well, notice that these terms are all greater than if these were all negative, and these are all less than if these were all positive. Or in other words, I note that -1 to the power n over n, if all of these were positive, then they would be either exactly the same as they are now, or they would be greater than what they are now, right? If this was +1, well, it would be greater than this. If this was +1/2, well, it would be the same. So here, all of these terms are going to be less than or equal to if they were all positive. All right? But since some of these are positive, they're greater than if they were all negative. So here, that's going to be between -1 over n and 1 over n. All right? If you're having a hard time seeing that, you can list out the first few terms of this one, list out the first few terms of this one, and compare. And you'll notice that the terms are always bound between these two. These are always bound between these two. But now I know I can take the limits of both of these. If I take the limit as n approaches infinity of -1 over n, again, what I should be thinking of is here, think limit as n approaches infinity of -1 over x, which of course is, that should be limit as x approaches infinity of -1 over x, and as x approaches infinity, this whole thing will approach 0. And so that means that that limit's going to be 0. If you want the limit as n approaches infinity of +1 over n, well, again, you should be thinking of the discrete case. You should think, oh, what is the limit as x approaches infinity of +1 over x? Which again, this approaches infinity, so this whole thing will approach 0. Okay. So here we have the nth term of a sequence is locked in between the nth terms of these two other sequences. But now, these two other sequences have their nth terms approach 0. So, by the squeeze theorem, we have that the limit of this one must be bound between the limits of these. The limit as n approaches infinity of minus 1 over n is less than or equal to the limit as n approaches infinity of minus 1 to the n over n is less than or equal to the limit as n approaches infinity of 1 over n. And since both of these on the n's are 0, that means that our limit that we want must be 0. Just like that. In fact, this conclusion of the squeeze theorem can be used directly in a slightly simpler form for many sequences, in particular ones that oscillate like the one we just saw. Here we have a theorem which states that if you have a sequence, a sub n, with the nth term a sub n, if we have that the limit as n approaches infinity of our a sub nth term's absolute value, if that's equal to 0, then the limit as n approaches infinity of the original sequence must also equal to 0. This one is proven directly by using the squeeze theorem. Note that a sub n is got to be less than or equal to the absolute value of a sub n. Right? Because if this is already positive, well, then they're equal. If this is negative, well, this one will be positive. So this one will be greater, which means this one is lesser. Okay? But also, this must be greater than or equal to the negative of the absolute value of a sub n. Because again, if this one's negative, well, then these are equal. And if this one's positive, well, then it's got to be bigger than the negative. Oh, but the limit of the absolute value of a sub n is equal to 0. So the limit of as n approaches infinity of minus absolute value of a sub n is got to be less than or equal to the limit as n approaches infinity of a sub n, which has to be less than or equal to the limit as n approaches infinity of the absolute value of a sub n, like that. Well, we know this one's equal to 0, just like this. But now this one, well, remember that we have properties of the limits, one of which says if I have the limit of a constant times something, I can just pull the constant out. That's linearity. Well, that's what a negative is. It's negative 1. So here, this one is the same as saying the negative 1 times the limit as n approaches infinity of the absolute value of a sub n, which is going to equal to negative 1 times, well, that's going to be 0, which will be 0. Okay, so that one on the right-hand side is 0, and this one on the left-hand side is also 0. So by the squeeze theorem, that means this limit must be 0. So by the squeeze theorem, that means our limit as n approaches infinity of a sub n is equal to 0. So if you assume this is true, then that must be true as well. Notice that this must actually be 0. If the limit is equal to anything else, this doesn't work. You can't say if this limit is equal to 1, then this limit's equal to 1. Why not? Because here, what makes this work is that 0 and negative 0 are the same number. If this was anything other than 0, let's say this was 5, this one would work out to be negative 1 times 5. So your number would be locked between positive 5 and negative 5. And since that means those limits are not the same, then that means that the squeeze theorem would no longer apply. The squeeze theorem requires both of those limits to be exactly the same. And here, if one is a positive 5 and one's a negative 5, or one's a positive 12, the other's a negative 12, that doesn't apply. So here, this must actually be 0. No other number will work. So for a quick example of that, let's take the limit as n approaches infinity of, now here, the example is a little anticlimactic because you kind of already know the answer, right? You know it's going to be 0. So here, let's make it a little bit more worthwhile by not seeing a very obvious example. Here, the answer is going to be 0. Obviously, that's what the theorem says. But let's give one that requires just a little bit of work to get there, or at least one that's not immediately apparent. So let's say I want the cosine of n pi over n squared. Now that one doesn't look at all like what I would have thought. Well, what is that cosine? That's going to be hard. Right? Well, let's consider what the terms look like. There's going to be some times where the nth term is going to be very convoluted looking. But if you write out the individual terms, you might see a pattern that, while difficult to describe mathematically, written out as a sequence of terms, might make things a little clearer. The other way will also be true. Sometimes you'll have a sequence of terms where the numbers themselves are very convoluted to work with, but writing it as the nth term will make things a little clearer. So it's nice to be able to go back and forth. Here, let's consider this as a set of terms. Let's go ahead and write out the sequence cosine of n pi over n squared. And here, let's just write out the first few terms. All right, well, if n is equal to 1, that's the cosine of 1 pi over 1. If I have the n is equal to 2, that's going to be the cosine of 2 pi over 2 squared is 4. Then the cosine of 3 pi over 3 squared is 9. And then the cosine of 4 pi over 4 squared, which is 16, and so forth and so on. Just like that. Right? Well, now, cosine of pi, well, that's negative 1. And cosine of 2 pi, well, that's positive 1. And cosine of 3 pi, well, that's negative 1 again. So here, as convoluted as that might have looked to begin with, it's just minus 1, comma, positive 1, comma, negative 1, comma, positive 1. Oh, it's an alternating sequence. This is going to be a useful tool whenever you see something that I don't know how to handle. Oftentimes, it helps give you a bit of intuition to actually just write out a few terms, and that might often help you to see what happens. So notice here, now I can pretty apparently use my theorem. Because here, if I take the absolute value of a sub n, that limit's going to be easy to find. Hey, if I take the absolute value of the cosine of n pi over n squared, and if I make a sequence out of those, well, that's just going to be the absolute value of these. Oh, but now that's just makes them all positive. So it's going to be 1 and 1/4 and 1/9 and 1/16 and 1/25, and so forth and so on. Or in other words, it's going to give us, well, that's just always 1 over n squared. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and so forth. Oh yeah, but now I know what this one converges to. But the limit as n approaches infinity of 1 over n squared. Again, you should be thinking the limit as x approaches infinity of 1 over x squared, which is going to give you 0. Okay, so if I take the limit of the absolute value, I get 0. But by my theorem, if the limit of the absolute value is equal to 0, then the original limit was also equal to 0. So that means that the limit as n approaches infinity of the cosine of n pi over n squared is going to equal to 0. This will be helpful whenever you have alternating terms. Plus, minus, taking an absolute value will be nice and useful. Now, keep in mind that's only if this ends up being 0. If this ends up being something other than 0, we haven't learned anything. That doesn't mean that this doesn't have an answer. It just means that this theorem is not the right thing to use. So that is our result. Now, I mentioned a moment ago that whenever you have the nth term, sometimes it'll help if you write out an actual list of terms of your sequence. But other times it'll help if you have a list of terms to write them as the nth term. It's useful to be able to go both ways. But in order to write this like that, you have to have a few patterns that you recognize in here. So what are those patterns? Well, there's a lot of them, but there's going to be a few of them that appear fairly often. So let's go ahead and just give a list of some common patterns that you might use, that you might see, and then we'll see an example or two of how you might use those to write the nth term of a sequence. So we've already seen the alternating pattern. The alternating pattern can happen one of two ways. If you have 1, minus 1, plus 1, minus 1, plus 1, ... Or you might have minus 1 first, then plus, then minus, then plus, then minus. So they're both alternating back and forth between a positive and a negative. If the first term is a negative, here we've already seen that one a couple of times. That is minus 1 to the nth power. Because if n is 1, well then negative 1 to the 1 is negative 1. And that's the first term. If the first one's positive, what you want to do is you want to have negative 1 to the power n plus 1. Because now, if n is equal to 1, 1 plus 1 is 2. And negative 1 squared is positive 1. If you want the second term, then n is 2. 2 plus 1 is 3. And negative 1 to the third would be a negative 1. Just like that. If you have the terms 1, 2, 3, 4, 5, just the numbers in order, that's usually described by just saying n. Because the first term is 1, the second term is 2, the third term is 3. So just the nth term is n. All right. If you have the pattern 1, let's see, what should we do next? Let's do 1, 4, 9, 16, 25. Those numbers would be n squared. If you have 1, 8, 27, 64, and 125, that would be n to the third power. Because here 1 to the third power is 1, 2 to the third power is 8, 3 to the third power is 27, and so forth and so on. Now, it's also fairly common to have not just the polynomials, but also the exponentials. In other words, flip these. So if you had 2, 4, 8, 16, 32, and so forth like that, that would give you not n to the 2, but 2 to the n. And if you had 3, let's see here, 3, 9, 27, 81, 243, that would be 3 to the n. Just like that. Now those might seem a little obvious. The next one is one that you probably don't see very often. 1, 2, 6, 24, 120, and so forth and so on. These are the factorials. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. Remember how factorials work? They are just the products of the numbers starting from that digit down to the number 1. So 1 factorial is just the number 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. Or 1, 2, 6, 24, 120. So that would be the nth term factorial. Just like that. You will sometimes see even numbers, 2, 4, 6, 8, 10, and so forth. The way to write even numbers is to say, well, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8. Oh, it's just double the position that they're in. So that's 2 times n. You will sometimes see odd numbers, 1, 3, 5, 7, 9, and so forth. Oh, well, those are the same as the even numbers, but you subtract 1 from those. Okay, so that's going to be 2n minus 1. Like that. And finally, be mindful of the fact that you won't always have exactly these numbers, even though you might have the same pattern. So for example, you might have a sequence that looks like 2, 9, 28, 65, 126, and so forth and so on. Here, this isn't one that is different from any of the other ones we've seen. Rather, if you look through these, you'll realize, oh look, these are the same as these, but off by 1. If you add 1 to 1, you get 2. Add 1 to 8 gives you 9. Add 1 to 27 gives you 28. 64 plus 1 is 65. 125 plus 1 is 26. So here, this would be the same as n to the third, but then you've added 1 to all of them. This one is not one that you need to remember, but here this one is, notice, you can have a known sequence. Here, my handwriting is getting worse throughout the day. You can have a known sequence offset by a constant. So keep in mind that not only will you have these patterns necessarily, but you may also have these patterns offset by a little bit. Oh, it's the same as these numbers, but you've added 5 to all of them. Or it's the same as these numbers, but you've divided them all by 3, or something along those lines. So you would take the rule for that pattern and modify it accordingly. So let's take a look at an example of something like this. So for example, let's go ahead and start off with a sequence that's not defined by the nth term, but rather just as a list of the first few terms. So let's take the sequence a sub n to be given by 7, comma, negative 7 halves, comma, 7 over 6, comma, negative 7 over 24, comma, 7 over 120. Okay, so, dot, dot, dot. So first of all, we notice that our numerator is always the number 7. So whenever you have a constant that appears, there's no rule for that. It's just that constant. So here we can write that as just the number 7. Okay, the number 7 always appears in our numerator. But what else? Well, notice that aside from the 7, we do have a sign, but it's not always the same. It oscillates. Here we start with a positive, and then a negative, and then a positive, and a negative, and so on. So if we look back at our list, the way we write an oscillating set of terms, starting from positive, is going to be negative 1 to the power n plus 1. So here that's negative 1 to the power n plus 1. That makes that positive, negative, positive, negative times the number 7. And now all of that is getting divided by, you say, well, that's not divided by anything. Well, you could also think of it as being divided by the number 1. So I have the numbers 1, 2, 6, 24, and 120. And in fact, that is a set of numbers off my list. 1, 2, 6, 24, and 120. That's the nth term factorial. So that would be my denominator. And that covers everything. That covers the changing signs. That 7 is the constant that appears in my numerator each time. And n factorial is my set of denominators. And there we go. We have, I guess I should have written the directions up here, right? write the sequence by defining its nth term. Instead of writing out just here are the first few terms, here we have a generic one. The advantage of this one is that we could find any term now. If we said, oh, I want to find the 17th term, well, then I could plug in 17 there and 17 there, and that's my answer. Right? But also because now this is formulaic, I have, oh, my nth term is this. This will be prone to being vulnerable to all sorts of tests and algebraic manipulations so that we can do things to this where over here it might have been a lot more complicated. Now, some of them might not be quite as apparent as this. They don't quite stand out as much. This trick is to experiment a little bit here. Let's do the same thing. Here I'm going to say the sequence B sub n is given by 2, 24, 720, 40,320, 3,628,800. Here I'm not going to put commas in here because otherwise that starts to kind of blend together. It looks a little strange. Now at this point you may wish to pause the video and give this a try. As strange as these numbers look, you will note that I've given you a list of things that you can try. I do guarantee you that the result is something that's from this list. However, since it's obviously not one of the ones that's listed here, it's got to be one of the ones that's listed that's been modified in some way. So go ahead and give this a try. Pause the video, try a few combinations of things, and see if you can come up with something. Once you think you've gotten a good answer, go ahead and unpause the video, and we'll go through it together. All right, so let's go through it. So here, these numbers, they're not really apparently anything right off the bat. Keep in mind that for some of these, you're going to just have to try a few different things. Here I have the advantage that I have a pause button on my computer, which means I can actually pause the video and I can try a few different things until I find the right answer. Here, just in the interest of full disclosure, I didn't immediately get the right answer. I tried a few different things, and that's okay. That's part of how this works. My first thought was, okay, well, it looks like these numbers divide into each other. At least these. I couldn't do that in my head, but these look like they divide into each other. So if you divide 24 by 2, well, you end up with 12. Right? So here, this is 2 times 12. And then if you do that again, that's going to be 720 divided by 24. And that does work out to be a whole number. That's 30. And then that one was 56. 720 times 56 is 40,320. And then if you multiply that by 90, that is going to give you that number. And I had to do that one. I couldn't do that mentally. Yeah? So now here, I look at these numbers and I say, well, okay, that's something. I mean, they did not give me a remainder. These do divide into each other. But yet these numbers aren't apparently anything. I don't see any nice pattern between them. At first I thought, it's a little, again, in the interest of disclosure, my first thought was, oh, these are all divisible by 3. And then I followed that vein for about 4 or 5 minutes before I realized, oh, wait, no, 56 is not divisible by 3. So that was not true at all. I started by dividing, and I thought, okay, maybe these are powers of something. Obviously, it's not any of the powers that are on my list, but maybe it's offset by some amount. But, well, after trying a few combinations, yeah, I didn't actually get anywhere. So what eventually did work out was it took me a couple of tries. It was actually my third try when I realized, oh, wait a minute. Some of these numbers I see on my list, even if they're not immediately next to each other. Notice I have 2 and 24. Well, those are the numbers on the factorial list. I have a 2 right here and a 24. Well, that's the second one. That's the fourth one. I wonder what the sixth one is. So I went through and I said, let's find 6 factorial. And in fact, that was 720. So now I had a pattern going. I know for a fact that's 2 factorial. And I know for a fact that's 4 factorial because I saw them both on my list. 720, it wasn't on my list, but once I saw these were 2 factorials, I thought, well, it's worth a try. And sure enough, this is 6 factorial. And then I thought, well, what about 8? And yeah, sure enough, that works. So here, these are 2, 4, 6, 8. They're the even numbers with a factorial on the end. And this one is 10 factorial. So we can write out the sequence by defining its nth term. If we go back over here, we see how we can define even numbers. 2, 4, 6, 8, 10. Those are the numbers that I need here. 2, 4, 6, 8, 10. And I do that by simply taking double n. Oh, but I want to take those even numbers and take their factorial. Okay, so take those even numbers and take their factorial. Here, this is defined as 2n factorial. Here, this is a little bit ambiguous. Depending on who's reading this, they might say, oh, take n factorial and double it. Or they might say, take 2n and take its factorial. And you say, well, that's silly. I mean, use the order of operations. Right? We should know what order of operations are. We should know what goes first. Well, yeah, but where does factorial fall in the order of operations? Parentheses, exponents, multiplication, division, addition, subtraction? I mean, I guess it's multiplication, but I mean, is there a difference? So here, let's not get into semantics about which one should go first. Whenever you use a factorial, parentheses are your best friend. Here, this is the 2n factorial. If you do n factorial doubled, that gives you a different set of numbers. If you take n factorial and you double it, it's going to give you 2, 4, 12, 48. Those are not the numbers you want. So here, it's 2n, and that is what you're taking the factorial of. So whenever there's factorials, don't leave any room for interpretation. If these are meant to go together, put in parentheses around them. If they're not meant to go together, then write 2, and then in the parentheses, n factorial. Don't leave any room for ambiguity. Finally, let's go ahead and wrap up this section with a few definitions that are necessary for this final theorem. Let's let A be a sequence such that all of its terms are non-decreasing. By what we mean by that is A sub n is less than or equal to A sub 2, which is less than or equal to A sub 3, which is less than or equal to A sub 4, and so forth. In other words, every term is going to be bigger than the one before it, or maybe equal to the one before it. So the sequence always increases or stays the same. It never decreases. It's non-decreasing. Or the sequence could be non-decreasing, or it could be non-increasing, meaning its subsequent terms are going either decreasing or staying the same. If the sequence does either of those things, then we call it monotonic. All right? So monotonic just means it's either always going up or is flat, or it's always going down or flat. Okay? A sequence, A sub n, is said to be bounded above when there is a real number m such that A sub n is less than or equal to m for all n. Visually, all that means is, oh, your sequence is bounded above if all of your points of your sequence never get any higher than some particular value. Now, maybe it works like an asymptote, or maybe the points actually start to just go back down. It doesn't really matter. All that we mean by bounded above is there is some upper ceiling, some place where your function will never get, your points of your sequence will never get any higher than that. A sequence is said to be bounded below when there is a real number n such that n is less than A sub n for all real n. So here, it's the exact same illustration, but upside down. When we say something is bounded below, we mean your points of your sequence, they might go down or they might go up, but there is some number which gives you a horizontal line on your graph. We call that number n, such that your graph never gets below that. So that's called a lower bound. Bounded below means it has a lower bound. Bounded above means it has an upper bound. All right, so now we need both of if we have both of those, then we say the sequence is bounded. And here, that's bounded. Okay, so the sequence A sub n is bounded when both of these things are true. It's bounded above and below. Okay, so that brings us to our theorem here. Let A sub n be a bounded monotonic sequence. So it's bounded above and below, and it's monotonic. It's either always non-increasing or it's always non-decreasing. If both of those things are true, if it's bounded and monotonic, then our sequence is convergent. The proof of this, we could go through it, but the sketch of the proof of this is not really very deep. And the formal proof of this requires the completeness axiom, which is an axiom in analysis or topology, depending on your background. Suffice to say, to go through this in full is very complicated, and to shorten it kind of does it a disservice. It doesn't really show you what it means. So rather than to do either of those things, here I'm going to say this proof is best left for a different kind of course. And here we're just going to accept this, and we're going to view some examples of this. All right, so the proof of this one will be omitted. So let's just take a look at some examples of this. So let's consider a sequence given by its nth term, and let's ask whether or not the sequence is bounded and whether or not it's monotonic. If it's both, we know it's convergent. If it's not both, well, then it may not be convergent. Now notice I say it may not be monotonic. Maybe it is, maybe it's not. The theorem says if it's bounded and monotonic, it's convergent. The other way is not true. If it's convergent, it doesn't have to be bounded and monotonic. There are plenty of functions that are neither of these things, but are still convergent. So here, just be mindful of the direction of the theorem. If it's bounded and monotonic, then you know it's convergent. But if you know it's convergent, that doesn't say anything about being bounded or monotonic. So in any event, let's consider the example given by a sequence whose terms are given by A sub n is equal to 3n over n plus 2, like this. And the question is, determine if the sequence is bounded and monotonic. Okay, so let's see here. First of all, let's see if it's monotonic. First of all, let's just plug in a few numbers. Now, here, if I was going to write this out, I would just start by popping in number 1 and 2 and 3 and 4. So let's see here. If that's 3 over 3, if n is equal to 2, that's going to be 6 over 4. And then if n is 3, that's going to be 9 over, let's see, 3 plus 2 is going to give me 5. And then 12 over 6, 15 over 7, and so forth. Here, let me reduce that. That might make things a little easier to see. That's going to be 1. That's 2/3. That's 9/5. That's 2. And that's 15 over 7. So now, right off the bat, I can tell that that is not going to be monotonic. Because notice, this decreases first, and then it increases. It goes down and then up. So here, monotonic means it's always either non-decreasing or non-increasing. Right? It's only going either staying constant or going in one direction, either up or down. But here it goes down, and then it goes, oh, wait, no, it doesn't. That reduces to 3/2. So my statement still stands in general, but here I reduced that incorrectly. So here, in fact, it does look like it's increasing, right? 1 is a little bit less than 3/2, and 3/2 is less than 9/5, which is a little less than 2, and so forth. So at this point, you say, oh, okay, so then clearly that's monotonic. It's increasing, which means it's non-decreasing. Well, no, because maybe it's only increasing right now. Maybe if I keep going 1,000 steps, then maybe it'll start to decrease again. So here, if I had found that it was increasing and decreasing early on, well, then I could say it's not monotonic. But if it is monotonic at first, well, I still don't really know. All right. It's not automatically disqualified. So maybe it is monotonic or maybe it's not. So that would have been an easy way to get an answer if it had actually oscillated. But since it doesn't oscillate, now we actually have to confirm that it's monotonic for all terms. So what we want to do is we want to just consider two different terms. Let's consider the nth term and the n plus first term. Consider a sub n and a sub n minus 1. Oh, sorry, plus 1. All right, that's the nth term, which is going to be 3n over n plus 2. And consider the n plus first term, which is going to be 3 times n plus 1 over n plus 1 plus 2. So here, this n is simply becoming n plus 1, which I could rewrite as 3n plus 3 over n plus 3. All right, n plus 1 plus 2 is n plus 3. All right, so now it looks like my nth term is less than my n plus first term. But maybe it just looks like that. Maybe it's true only for a while. Maybe eventually that reverses. So here I'm going to test that hypothesis. After all, here I have the nth term, and here I have the n plus first term. So I think, I'm not sure, but it looks like the a sub n term is always less than or equal to a sub n plus 1. Now, if I can confirm that's true, then by definition, this function is monotonic. It looks like it's true, but we have to check it. All right, well, let's go ahead and do that. We think, well, then that means that we think that 3n over n plus 2 is less than or equal to 3n plus 3 over n plus 3. Well, I don't know. Is that true? Well, let's confirm that. Here, this looks a little complicated because here I have rational expressions. So let me multiply on both sides by n plus 2 and n plus 3. We multiply on both sides by n plus 2 and n plus 3. In other words, by my common denominator. Now these go away and these go away. And so I'm left with, again, I'm not sure if this is true, but I suspect that that's going to be, well, let's see, 3n times n plus 3 is less than or equal to 3n plus 3 times n plus 2. Okay, well, that's a little hard to see, but let me go ahead and distribute this. This will give me 3n squared plus 9n, 3n squared plus 9n, less than or equal to, if I distribute this part, I'm going to get 3n squared plus 6n plus another 3n will give me 9n. And then 3 times 2 will give me 6, which is true. Because look, this is 3n squared plus 9n. And this is 3n squared plus 9n plus 6. Here, these two are the same. So if I were to subtract this from both sides, I would end up with the statement 0 is less than or equal to 6. But that's true, which makes this true, which makes this true, which makes this true, which makes this true. Oh, okay, so I've confirmed that. Oh, okay, so then it must be true that no matter what n is, right, because here we didn't matter what n was, this is true for any n, an is less than or equal to an plus 1. And so by definition, that means that my function is non-decreasing, and so is monotonic. So the sequence a sub n is non-decreasing. And so by definition is monotonic. So if you're trying to prove something is monotonic, first list out the first few terms of the sequence. If in the first few terms it's not monotonic, well, then you're done. It's not monotonic. But if it is, you haven't proven anything yet. You only suspect that it's true. You have to prove it by showing that it's true for all values of n. Okay, so that's half the question. Is it monotonic? Yes, it's monotonic. Now let's talk about boundedness. Is this value bounded? So here, let's rewrite the sequence. Here we have a sub n is equal to 3n over n plus 2. Just like that. Now remember, for a function to be monotonic, or rather for a sequence to be monotonic, for a sequence to be bounded, rather, it has to be bounded above and below. Well, one of these is easy. Is it bounded below? Well, sure, because after all, this is a monotonic non-decreasing sequence, which means since it's non-decreasing, the terms can never go down. They have to keep going up, which means that the smallest term must just be the first one. Oh, okay, so that means that since these are going to keep going up forever, the smallest one must be 1. So sure, it's bounded below by the first term. Okay, so that one's easy. Anytime you have a monotonic sequence, one of the bounds is easy because it's always going to be the first term. If it's non-decreasing, then your first term is what bounds it below. It's the lower bound. If it's non-increasing, then the first term is bounding it above. All right, so that part's easy. Now let's look at the other one. It's bounded above. Well, let's see. This 3n over n plus 2, it's a number. Here, because it's a number, I can manipulate it. All right? It doesn't have to be a whole number. Notice right here, n has to be a whole number, but the number itself can be any real number there. So I can manipulate this, and I can divide the top and bottom by n. So since n cannot equal to 0, we know n is 1, 2, 3, 4, 5, and so forth. Here, if we can divide top and bottom by n, that's perfectly valid, and that'll get us 3 over 1 plus 2 over n. All right, just like that. So here, notice that this is some positive number. Now, the bigger n gets, the smaller this is going to get, but that doesn't matter. It doesn't matter how big n gets. This is always going to be some amount, maybe a very tiny number, 2 over 1,000, 2 over 1,000,000, 2 over 1,000,000,000, but it's going to be some amount, which means this denominator will always be 1 plus something, which means that we're going to be dividing by 1 plus something. If that plus something wasn't there, that would be 3. Oh, but that is there, which means you're always going to be dividing by a little bit more than the number 1, which means this will always be a little bit less than the number 3. All right, so here this is always positive. All right, which means that we're dividing by 1 plus some little tiny amount, which must be less than 3 over 1. All right, if you have extra stuff in your denominator, that makes it smaller than if you didn't have that extra stuff in your denominator. Oh, but now that tells you that it's bounded above by 3. Every term in your sequence is bounded above by 3. All right, so my sequence is bounded below by the number 1. It's bounded above by the number 3, and it's monotonic. So it is bounded. And even though it doesn't ask the question, but here you do confirm that it's monotonic and bounded. So we confirm that A sub n is convergent. And that makes us happy. And that concludes our section. So for exercises, section 9.1, you should try problems, just all of them. Just do everything. Try problems 1 through 59, every other odd. And so here, since it's every other odd, you would do number 1, number 5, number 9, every fourth problem. Here you would normally skip over the number 3, but here actually 1 through 59, every other odd, and also go ahead and do the number 3. It's a conceptual problem. It's not a computational one, but it is an important concept to know for later on down the line. So that is it for the exercises of this section, and that is it for the section itself. If anybody has any questions, please let me know, and I'll get back to you as quickly as I can. I hope you all have a good evening.